Okay, so hi everyone. Thank you very much for being here and still being interested. So today is about chapter 3, and we're gonna get our hand a bit dirty, I guess. So I'm looking forward to it. And like last time, I'm recording this presentation, and it will be available on the YouTube channel of the KGC conference afterwards. So Giuseppe, Alessandro, the floor is yours.
Thank you very much, Matthias, and welcome to this new meeting related to the Knowledge Graph Applied book. As introduced by Matthias, today we will present the chapter 3 of the book, which includes the first code examples to start to do your end on the code. The title of the chapter is Create Your First Knowledge Graph from Ontologies. And basically, these are the main points that we will touch during this presentation, and actually during the full chapter when you will read it. So basically, we identify in order to build our knowledge graph the business goal as the main driving principle, right, to create the knowledge graphs. So basically, before starting to put our hands on the code, we will try to understand in the best way as possible what is the business goal that we want to reach. Then we will try to select the best technology in order to represent our knowledge graph, considering the use case that is related to this business goal. And then after clarify this aspect and make the best decision in order to create our knowledge graph, we will try to construct something that could be useful in order to support the clinician's activity. So before going into the details, I would like to make a recap of the CRISP-DM model that has been presented last week by Alessandro. So basically, this is the model that we will try to keep in our mind when we face any problem related to the knowledge graph construction, evaluation, deployment. And this is an iterative approach, right, in which some of the main phases for the knowledge graph creation includes the business understanding that we already mentioned, the data understanding, the data preparation phase, and also the knowledge graph model creation and update. So basically this part. And considering this subset of this CRISP model, we will try to progressively create our mental model that describe the full problem that we want to address and how to resolve this problem. So basically, we'll try to define the right approach for each of these blocks, which are actually the subsets, a subset of the phases described and introduced by the CRISP-DM model. So as we already mentioned, the first step is the business understanding phase. So in our case, the target persona of the knowledge graph or of any application that leverages our knowledge graph is the clinician, right? And among all the activities that involve the clinician, one of the most important is to diagnose and treat diseases based on the detected symptoms from the patient. Actually, in this specific domain, more technically, the detected symptoms are recognized as anomalies in the phenotypic features manifested by the patient. In order to clarify this concept and to make a simple example, let's think, for instance, about the common cold, right? That is characterized by distinct phenotypic features, which include, for instance, fever or fatigue and etc. And the fever and fatigue are actually true phenotypic features that can be that actually can characterize other conditions. So this is just a simple example in order to understand what is our application domain in this case. So one of the most complex activities considering this domain description for the clinician is to identify a disease based on the phenotypic traits, right? In particular, in the case of rare syndromes. So this is one of the most complex problems that the clinician has to address. So our goal in this case is, considering this specific aspect, is to create a tool, or actually in our case, building a knowledge graph that is able to support the clinician in this complex activity. The second main phase is related to the data understanding. And actually, the clinician plays also a fundamental role in this context, because he or she can be considered the domain expert in this case, right? So basically, it can also suggest some of the data that can be useful in order to support his specific or her specific activity. And considering our main goal, we decided to use some of the resources that are available from the Human Phenotype Ontology platform, right? Which is a platform that includes a lot of data sets related to this specific domain. And for our basic example, we will use two distinct main resources, right? The first one is the HPO ontology itself, which provide a contextual description of the phenotype domain. In the next slides, I will provide you some details about this, how this knowledge is represented within ontology. While the second one is a data set. It's just a TSV file that is annotated using this HPO ontology. And this data set actually is a collection that describes the relationship between these phenotypic features and the related diseases. And we will see that a key information in this relationship is represented by the source and the date of the source from which this relationship is created, because we would like to guarantee that the clinician, during the exploration of the knowledge graph, is able to go to the original source in order to check the information from the source, right? So basically, from the starting point. So we would like to keep this information available in the knowledge graph in order to enable the clinician to check this specific aspect. So let's go into the details about the resources that we have mentioned. So basically, one is the human phenotype ontologies that provide standardized and semantic information on phenotypic anomalies. And basically, all the phenotypes that are mentioned as nodes in this ontology are collected according a hierarchical structure, right? So basically, a tree. So for this reason, according to this tree, if having a certain or manifesting a certain phenotype implies that you are manifesting also phenotypes that are located on top of the hierarchy. So this is just a very simple example. If the phenotype detected is tall stature right here, then you obviously have also an abnormality of body height. Just to clarify this aspect, that you have also to consider the top level nodes in the hierarchy, right? So not only the detected phenotypic feature in a specific node. And actually, this human phenotype ontology is providing using RDF and XML. And so later in the code example, we will see how we can import this data and how we can apply some changes that can help us to reach our goal. An interesting point of this human phenotype ontology is that there are some, let me say, gray areas, because if we consider some specific cases like type 1 diabetes, actually in this ontology, this disease or this entity is at the same time actually is represented both as phenotypic feature, both as a disease which has some related phenotypic features that are common in people that are affected by type 1 diabetes. But in some other cases, this is considered a specific phenotypic feature which characterize some rare syndromes. So consider this twofold representation of type 1 diabetes. We should consider also this aspect during, for instance, when we perform, for instance, query on the knowledge graph. And discovering this specific characteristics of the ontology is also obviously part of the data understanding phase. And the second main resource is represented by this TSV file, which provided actually different properties that are related to the relationship between a relationship between a disease in this case and a phenotypic features. Actually, these source provide also some modifiers that are able to specify the nature of this relationship. For instance, the onset age or the frequency of a specific feature, considering the syndrome that we are analyzing, and also who is the, for instance, the author that annotated this specific relationship. Because obviously this information that a specific phenotypic feature is related to that disease can directly come from, for instance, the synopsis of the description of the disease, but sometimes, especially for new publications, then new publication can describe and report that a new phenotypic feature can be associated with a specific disease. So basically, we should understand who is the author of this annotation and what is the original source from which this information has been retrieved. And during the loading, right, of this data, in particular this second resource, we should apply the so-called mapping, right? So basically, we have a table representation. Here on the top, you have a simplified version of the previous table. And then we have to decide how to map this information into a graph structure. So according to the use case that we are discussing, we would like to take the information very compact, right? As much compact as possible. So basically, in this case, we will define the phenotypic feature and the disease as the two main nodes, right? So this is the phenotypic feature node, and this is the disease node. And we would like to incorporate all the properties that are that describe the nature of this connection within the relationship. So we define that a specific disease is characterized as phenotypic feature, a specific phenotypic trait. And in this relationship, we store, for instance, the source of this information. We store the author of this annotation, and also the creation date. So basically, the key information that describe the nature or that describe the reason behind this relationship, we would like to store this information in as properties of the relationships. This is the key point. And this is why in the chapter we also discuss some of the limits of the standard RDF to model this type of information. So to model the properties of the relationships. Actually, as we already mentioned in our previous meeting, with RDF star, we are able to actually model in a very straightforward way the properties of the relationship. But in traditional RDF, there are some limits. And here we report some examples on that are related to the workarounds that are adopted in RDF to represent this type of information. And maybe I can discuss a bit quickly each of these examples. The first one on the top left side of this slide is related to the reification that we already discussed in our previous meeting. And maybe it could be useful to clarify that reifying, the process of reifying means to write RDF statements about RDF statements. And in this case, ID1 is a resource that does not define an entity, but represent a statement by itself. And using this, the workaround, we can attach multiple properties like here to the graph edges, right? But sometimes this can create some inefficiencies in data storage or in the data exchange, because we should create additional statements, right, for representing the data. A similar problem happens in the case of NRE relations, right, in which you create, actually I use this approach many times when I work with RDF, but the main idea, the key idea is to create a new concept. This concept in this case is called annotation. And then we attach to this new concept all the properties that we need in order to define the nature of the relationship between a disease and a phenotypic feature. Actually, this type of representation can be easily interpreted and understood by the domain expert, right? But along the increasing complexity of the ontology, may arise some backward compatibility problems, especially when the data model evolves very fast and in a very complex way. Another possible way to represent relationship properties in RDF is adopting the so-called singleton properties. In this case, you can see that we attach to the relationship, for instance, an ID, and to each relationship with this ID, we will attach also again the properties related to the source, to the author, or to the date. Also, in this case, we can have some inefficiencies because we have to create a new relationship with a new ID anytime we would like to create an annotation. And a similar thing happens in the case of the name graphs. But in this case, we attach the properties directly to the named graph that includes the specific triple that describe the relationship between a disease and a phenotypic feature. So this is just some reflections that actually you can do before selecting the technologies that you want to apply for resolving your specific use case. So for this reason, we decided to go for the LPG in this case. Try to keep in mind also the approach that we introduced in our previous meeting. So just enough semantics. So basically, we would like to keep the schema of the data as simpler as possible, and just considering the subset of the ontology features that can be useful for in order to reach our business goal. And here I would like to start to show some code example. Let me check here, and I will try to follow the code that is available on the book to build the knowledge graph that can be useful for our purpose, because we understood the key aspects of the data. So the HPO ontology and the annotated data set, which provide the information on the relationships between diseases and the phenotypic features. And after this understanding process, now we can concretely ingest and manage the data. So I remind you that, okay, let me go there. I remind you that actually, in order to run this code, you will need Neo4j with some plugins including the Semantics plugin that we introduced also last time. But on the book, we will have a rich appendix that provide you all the details in order to install Neo4j, to load and install the plugins, and etc. So this is the basic requirement for your machine, but also in the chapter, we will find also further details about this aspect. So let's start with this empty database, right? And the first step, as I mentioned, I will try to follow the code that is available on the book. The first step is to configure our instance of Semantics, right? Because we have to explain how Semantics has to load the data, in particular the ontology data. So I will copy this code here. I don't know if it's enough visible or if I have to zoom in, but I can try to do that.
I think it's pretty good. I can see it well.
Okay, cool. So basically, here you can see 3 different call procedure, and 10s is the name of the library of the Semantics library in Neo4j. And here you can see that in the configuration, we define 2 key information. The first one is how we would like to handle the URIs, right? Because as you know, each resource in RDF is identified by a URI. And we should understand if in our specific case, we need to keep the root URI, so the URI that come from the ontology. Maybe this feature could be useful if we import multiple ontologies, because in that case, we would like to keep the original URI in order to define also the namespaces. But in this case, considering the fact that we would like to load only a single ontology, we'll put ignore value for this specific property, for this specific field. And this also will simplify also the information reading, right? Because we will see only the last part, let me say, of the URI. The second main configuration is called apply Neo4j naming. Actually, in the documentation, you will find also other fields that you can set for the ingestion process. But in this case, we will like to keep the standard way in which Neo4j in general represent the data. So basically, it usually applies a full capitalization for the name of the relationships, and the first capitalization letter for the labels, right, that are adopted. So we can run this command for the configuration, and here you can see a new node called graph config that store this configuration that will be used during the ingestion process. The second main phase is to actually ingest the HPO ontology. So this is the way in order to do that. So basically another call procedure. Let me go back here. A call procedure which is called import fetch, and here we report the URL from which we would like to download the data, and we define also how these data are serialized, right? In this case, RDF XML. The Semantics enable you also to load the data from disk, from your system, or also to explicitly provide the triples within this window in order to directly load the Obviously, this works in all the cases in which your number of triples is limited. Okay, I ran. It will take a while, actually just 30 seconds, but before the loading part, I would like to show you some key aspects of the ontology that will be loaded. As we said, our approach is just enough semantics, right? But here we can see that obviously the ontology, as most of the ontology that are describe a complex domain are quite complex, right? So on the right side of this slide, you can see actually the hierarchical structure that could be interesting for us in our specific case, which describe the hierarchy of the different phenotypic features, right? So for instance, the source, the top node in this case, here is diabetes mellitus, and the subclasses are, for instance, maternal diabetes or type 2 diabetes or type 1 diabetes, and etc. And obviously the ontology imports also all the metadata, right, that are connected using a graph structure to these specific entities. And in this case, we can see what are all the possible names that can be associated with type 1 diabetes. And actually, these names are also annotated using this specific relation. So basically, type 1 diabetes with the Roman character and the traditional character are some layperson terms, right? So basically, these are terms used by the layperson, while the insulin-dependent type 1 diabetes mellitus is just the technical terms. So basically, when we import the ontology, we have both this information. But as I said before, in this case, we don't want to construct a full knowledge representation of the clinical domain or the phenotypic domain. We would like just to get the information that can be useful to support the clinician activity. So this is our main, our key information, so the information that we will use to expand our knowledge graph. So it should be loaded. You can see here that more than 1 million of triples have been correctly loaded. And now the second main step is to try to enrich this information, right? Because actually, for instance, if I click here, HPO, actually, this information is empty for now because I didn't yet label using a Neo4j as a Neo4j label. I didn't still label the resources that I have loaded, right? So this is the code to do it that. Very simple. I will try to match all the resources that have been loaded that includes this specific URI, right? And I will also create a new ID to these entities in order to simplify the access to the information. So this is our second main step. And the third step actually will be the loading of the annotated dataset. So let me follow again the instruction variable here. And with this specific procedure, we can load information for any CSV type file, right? But in this case, considering that it is a TSV, we specify in this case what is called the field terminator. And using this specific procedure, actually I split the full procedure in most simple ones in order to also make this procedure more explainable. But basically with this procedure, I will load the diseases, right? Because right now I just loading the phenotypes, right? That are included in the ontology. But now I would like to load the diseases. So I run this command. It will require actually less than 10 seconds. Wait, and I would like to add further information. So basically now, if I click on disease, you will see that the diseases have been loaded, but there are no connection right now between diseases and HPO. I have to create this connection, and I will try to run another procedure here And this is the key information, right? So basically, I will merge the relationships in order to create an explicit relation between the phenotypic feature and the diseases. Okay, we should wait for a while. And right now, if you have any questions until now, I don't know if anything is clear or.
So we had some question in the chat, but Alessandro already answered. I don't know if you want to, I think they are interesting, so we can maybe tell them loud, and Alessandro, you can rephrase what you just said in the chat.
Yep,
Okay.
that's fine to me. But I mean, I would say that they are a bit unrelated to the specific topic. You know, this is a more generic.
Okay, we'll wait till
that we
the
can
end.
Take offline. Yeah.
Okay, perfect. So I think we don't have any specific question in the chat related to the demonstration right now.
Okay, so I can continue. So basically, with the last procedure that I ran, I created the explicit relationship between the disease and the phenotypic feature. So if I click on the disease here and I'm going to explode the node, here you can see the explicit relationship, right? Then we will see some example in order to have a better understanding of this. But this is something that we would like to reach, right? So create a connection between the disease and the phenotypic feature. And the last step in building our knowledge graph is to store the properties that describe this connection directly in the knowledge graph, and in particular as properties of the relationship. So I will run this last procedure. And actually, this is actually just processing. In the book, we will describe the details of each row of this code, but the most important part is, let me say here, because we retrieve the data from the TSV file, and using this data, we will store information like the source, the author, and the date of this annotation. So I think that actually we can remove this part because it is not so useful. And so at the end of this process, we will see that we were able to store all these details related to the author, to the date, and to the source within the relationships of the knowledge graph. So basically, if I click here and I expand a node here, now I should be able to see that here you can see that I was able to store this information in the relationship of the properties, right? So in the properties of the relationship. So the author, the date, and in this case, the source. Because if we search this on the web, actually, we can also add a URI in order to get directly the full link. But basically, this is the ID of the disease in this specific ontologies called ORPHA, which include the rare syndromes. So until now, we are build our knowledge graph, and now let's see if it is actually useful for our purpose. As we said before, we would like to support the clinician to identify the right rare syndrome or disease based on the phenotypic feature that he encounters, right? So in order to further clarify this example, we can see that the type 1 diabetes mellitus disease is connected to this specific phenotypic feature. So basically, if the patients manifest like something like polyuria or polydipsia and etc., basically this can be information that can be used in order to identify the disease. So basically, what we can do is provide the clinician to a way in order to get the right disease, specifying the phenotypic features. So imagine that the clinician, okay, he already diagnoses the type 1 diabetes, but he noticed also some specific features in a young patient, right? So including, for instance, growth delay, large knee, pruritus, and etc. So we can create a query that include all these phenotypic features and provide to the clinician what is the best diseases that actually is connected to all or to a subset of these phenotypic features. Obviously, this is a very straightforward example. I can understand that detecting diseases, it's a really more complex process, but this type of knowledge graph can support, right, the clinician in this specific task. So here we define all the phenotypic features detected by the clinician. And when I run this query, actually, I can get here the disease name and all the features that are associated with this name and the number of features that are actually associated. So this number is just a length of this array. But here you can see from this example that describing, putting the specific phenotypic features, I can get the related disease. So basically, maybe our patient is affected by this specific disease, considering all the phenotypic features that the clinician have been was able to detect it, right, during his analysis. And so this is a tool that in some way can support the clinician. You see how simple was the ingestion process. And as last example, I would like to show you how we can exploit the reasoning, right? Because in the last meeting, we also mentioned the reasoning part. And we would like to I would like to show you how Neosemantics include some of the reasoning features that are provided by the ontology. Let me run this Cipher query. And this Cipher query actually provide a subset of the tree structure. And basically all the subclasses of the abnormality of the endocrine, right? Because as we said before, the data is located into a structure, a hierarchical representation, and we would like to exploit this information. Because some of the diseases, actually, this is a bit freeze in some way. Let me move some windows here. And let me restart, rerun again the query. Okay, because actually some of the diseases will be directly connected to abnormality of the endocrine, right? But there are some also other subclasses, right? So basically, we would like to get all the diseases that are connected to the subclasses of abnormality of the endocrine. And this is a query that you can run here. And this is the key part, right? In which you describe which is the relationship that represents the hierarchical part. And here you have the relationship in order to get the diseases that are connected to the subclasses. And when I run this query, I should get the answer. That is this one. So this disease actually is characterized by some phenotypic features like parathyroid hyperplasia and hyperparathyroidism, which are some subclasses of of the abnormality of the endocrine system. So we exploit the hierarchy in order to get information that can be inferred, that is not directly related, connected to the abnormality of the endocrine system, but also information that comes from the subclasses. So this is a way to exploit the reasoning part using the new semantics. And maybe I can stop sharing and I can leave the stage to Alessandro and Fabio, and then if you will have other questions, we can discuss further this part.
Thank you.
I think there is one, Giuseppe, that you should try to answer, because there is a question about the provenance info, the author and the source, if it should be added to each individual relationship.
Yeah, it should be added to each individual relationship, because actually in the annotated dataset, I will show you maybe an example again of the data. You can see that for each connection that includes a disease, a disease here and a phenotypic feature, you have an author in this case. So each relationship which connect a phenotypic feature and a disease is characterized as being annotated by an author, right? So basically, you have an author information for each relationship that connects a disease and a phenotypic feature.
Yeah, please go again. Go ahead.
Yeah, so could you then also just create a publication note and put the information there and link to that from the relation?
Yeah, actually, this is directly stored in the relationship, right? So basically, you can get this information directly from the property of the relationship.
But can a property have a relation to another node where you store this information?
No, this is not
no.
possible.
No.
Yeah, that's what I meant, Elke. That's the reification thingy that I was thinking about as well, because then you would have a node in between to which you link, and then link to everything that relates to it.
Yeah.
And also what you said before, I think that's very much possible. If you have a paper which mentions a few things, you could then link either directly or indirectly through that reification to a certain property to to kind of structure the information in a way, in exactly that way you need for your type of analysis or storage.
Well, yeah, I mean, definitely the way in which we generally solve this issue is to sort of materialize a relationship, which means that each relationship is automatically converted in a node, and then the node acts logically as a relationship, and then you can, let's say, sort of create a sort of a hypergraph out of a normal graph, because here is the problem, that, for example, Neo4j, but many of these graphs available in the market are really just graphs, not hypergraphs, which means that you cannot connect a relationship with more than 2 nodes, more or less. But I mean, it's an easy problem to solve, because really what you do is just to materialize let's say the relationship, and then you can have as many connections as you want, to this specific relationship. So you can have the 2 nodes that you had before and the source. Of course, the other option is to, let's say, store a reference information in the relationship and then use it as a sort of ID, so without creating literally the connection, you can use let's say this to say, okay, the source is this ID, and in your application that that specific ID point to a source, and then from there you can continue your relationship, your navigation, for example. Of course, it will be a slightly different query, but both can work. And for example, in the case of Neo4j, thanks to indexes, it will be super performant in any case, because then we have always to come to this point, how much performant is a a model according to the type of navigation that you have to do. You know, that's why the real model, as we were discussing even in the chat, you know, really depends on what you have to do. There is no one graph model that will suit all your needs until you go through your use cases and decide, okay, this one could fit the needs, and definitely you can even replicate data that unfortunately is not the best practice, but based on our experience, sometimes you have no choice, you know, than just replicating data. And this link based on ideas, for example, is a clear example. You know, you are replicating the idea from one to the other. So yeah, I didn't check if there is another question for Marc-Antoine.
Well, it's more a comment, right? I mean, I totally believe in this reification of relations to get the hypergraphs, but the problem is then the Cipher queries become awkward, because if you want to do a path query, especially a recursive path query through a reified relation, you lose the Cipher operators are not as convenient anymore, and you lose performance as well, because the indexing for path transitive relationships do not go through reified relationships quite as conveniently.
At least
that's an interesting point.
Yeah, yeah.
Sure,
It is. In ArangoDB, you can define anonymous graphs to kind of select a smaller search domain if you're doing that type of path queries through the graph, which I find quite nice.
Well,
like,
that's an interesting point. Yeah.
Interesting.
Yeah,
Thank you.
just defining like, okay, I want you to search through these node and edge collections and only take these and look from starting point to end point, and then it will not search any further, and you give it a depth, and it's quite nice once you know what you're doing.
But it does not, this is a restriction, not an extension, right? I was complaining about the fact that reified path queries narrow the search and you lose. That's ArangoDB.
Yes, it is. And
that
yes, it's a constraint insofar as you tackle the problem of exploding search complexity by fencing off the search domain.
Still interesting. Thank you. I think it should be possible to have a kind of RDF inference rule saying if you have this reified relation, create this derived relation from it, and then that one can be made transitive.
I just want to make sure we finish, because I think this subject is very interesting, but very we're going deep down in the details, technical details. So.
Well, yeah, I don't think that we will cover all the chapter 4 in any case. I was thinking that I can just introduce it a bit, and then Fabio will share his part with Vlasta next week. So because Fabio's part will take at least 20 minutes. So definitely we won't have the time. So I will just do a short introduction of the chapter 4, leaving Fabio for the next time. And he will share the stage with Vlasta. Okay, let me share my screen quickly. So differently than the other chapters, this one is still not available. So we are speaking about something that you will most probably see in the next version of the book. We are in the chapter 4. We are continuing a bit on this topic, because as I mentioned last time, in the first part of the book, what we are doing is literally to discuss about, of course, the main concepts related to the let's say to the knowledge graphs, and of course, being a very practical by constructing certain type of knowledge graphs and helping the users, let's say, to the readers in this case, to really see how to use it, how to create it, and how to use it. So In this chapter 4, as I said, we will continue to build the knowledge graphs of different shape, I would say. In this case, we are building from almost structured data sources, while in the next part of the book, and this is something that you will see in the next session, we are building from unstructured data sources. So in this, this chapter will cover 3 major aspects or topics. So of course, the first one is creating a knowledge graph from existing structured and semi-structured data sources. Then something that we will do will be also to show how to characterize the resulting knowledge graph, because in the chapter 3, we've seen how to do some reasoning starting from ontologies imported in the form of level property graph. Here, instead, what we would like to do is to create a knowledge graph and run some analysis on this knowledge graph. So trying to teach the readers how to look at the graph and analyze it in a way that will allow them to see if it is good enough for the next stages. So it's a sort of preparation of what will happen in the part 3, in which the graph will be used as an input for advanced analytics, I would say. So it's important that after you create it, you sort of understand how it is structured, how the relevant areas that you are going to consider are connected to each other or are isolated from the rest, and so on and so forth. So that's what will be covered in the chapter. And as examples, again, we will continue on the line of the biological or biomedical knowledge graphs as use cases. And we will see specifically how let's say you can use what's already available, let's say in the market, what is a very easy accessible just by importing from, let's say in Neo4j, for example, but just to use what other people created. And we will see instead how complicated is to merge these different data sources, because, for example, they are using different names, for example, for the same disease, or they're using 2 different ontologies. So there is a full process of normalization. So we will take this biomedical knowledge graph as an example. We will see something that has been already created by someone else, and then we will go in detail and understand how this works. Again, once more, I would like to iterate on the concept of the CRISP DM approach to not only knowledge graph, let's say, acquisition, but also in general for the building of knowledge graph application. So again, when we are building a knowledge graph, whatever it is, we should always start from the business understanding and not from just importing all the data that we have, as we were discussing also today in the chat, and then say, okay, now that I have this knowledge graph, what should I do with it? It should start from a completely different point of view. Again, we have seen this as a common pattern of all the failing projects. So we will repeat this again and again to make it clear through the entire book that let's say the approach should be really starting with the needs, then define the data, import this data, normalize this data because this will be necessary, and then start with the analysis and the process. In terms of the biological or biomedical knowledge graph, and based on what I just said in terms of let's focus on the application, on the goal that you would like to reach, and then define the model. So we cover in the chapter 4 3 major applications related to the biological use case, biomedical use case. One is the multi-omic applications, and in particular, we will cover certain type of relationships and, of course, nodes, like the gene to disease for the genomic, the RNA with disease, that is what Fabio will show you next week. Or, for example, for proteomics, we have this protein-to-protein network that contains interaction between proteins and their connection with specific disease. Then we have in the pharmaceutical application many interesting use cases because generally let's say the main application here is the so-called drug repurposing, which means that starting from existing drugs and their connection with diseases, the drug repurposing aims at finding new applications, let's say, of existing drugs. And this is an interesting problem, not only because, of course, this has a relevant impacts on the life of everybody, and of course on the companies that could leverage this type of applications, but also because it covers an interesting, let's say, it leverages an interesting algorithm that is based on how to say this, a link prediction. That means that you can, based on an existing graph, identify missing links between nodes, and that's why this is very relevant for us, because it is the base for the part 3 of the book, in which we will discuss in detail many different applications, and specifically the link prediction among the others. And of course, this pharmaceutical application is very, very interesting because, of course, it requires to understand very well how compounds work, but not only how they interact with the genes, what are the side effects, or how they interact to each other specifically. And this is very helpful for tons of different applications in which, for example, you can find some specific, genetic, let's say, relevance for specific drug applications. And finally, there are clinical applications. Here, this is a totally different biomedical case, because there is an important variant compared with the others. Because if before, for the multiomics and pharmaceutical applications, they are very generic, so there is no, let's say, specific data related to patients. The clinical applications instead are interesting because they put the patient in the picture, and these help to create any complete set, a different set of applications in which you know exactly which kind of the treatments a specific patient let's say followed, and what is the final result, and see this as a pattern, and then check back against the let's say the literature or the well-known practices, for example. So this is an amazing source of let's say of knowledge. The only issue, and that's why unfortunately we will not treat it so extensively, is because of the let's say the complexity of the let's say the privacy here. So it's very, very difficult to find a relevant data set containing a relevant information at certain level that could be used for example, advanced analytics. So these are few of the problems that are described related to these biomedical applications. So in order to close, because we are running out of time, there is one aspect that I would like to stress on before leaving you for the next session. The basic idea that we would like to sell, let's say in the chapter 4, is really not only about the way in which you should approach the construction of the graph, the issues that you can face, like naming differences, entity linking and such, but how to objectively evaluate the results of the knowledge graph that you created, because of course you would like to look at a graph that in many cases is very big and extract some measures that will characterize it. So we use this chapter to start introducing many of these with concrete examples, with actual queries and analysis that allows you to understand what is the content of your graph. So imagine that you have a huge graph. How can you characterize it? Well, in this chapter, we would like to cover quite well these areas. So we use different measures. I listed here a few of them. Some of them are very famous, like WCC. So there's weakly connected components, and Louvain, that are, let's say, community detection algorithm. The main difference is that in the weakly connected components, you have a picture of the graph. So it just describes how many independent subgraphs you have in in your bigger graph, while Louvain is trying to optimize the modularity. So it is trying to maximize the connection among the elements in the cluster compared with the connections outside of the cluster. But apart from these that are very well known, we introduce something that is interesting, because it is completely, let's say, specific for not only diseases, but in general for this knowledge graph. So if weakly connected components and Louvain are applied to whatever graph you have, there are others that have a lot of sense if they are applied to knowledge graph. So for example, in the PPI network, so in this protein-to-protein interaction network, knowing for example, this relative size of the largest connected component is very relevant to understand how big is this pathway, for example. So for all of these measures that unfortunately we cannot cover in detail, you can pair how to say biological meaning. So for each disease, you can see what is the relative size of the connected components or the density of the cluster, and from this you can easily match with a biological meaning. So that's more or less what is covered, let's say, in the first part, while Fabio will give you a concrete understanding of how to build the knowledge graph. He will show you real code from notebook, and you can take the code and use it for reconstructing the same graph. And I think that's it for today. We are already 3 minutes out of time, so I don't want to continue, but this was exactly what I wanted to say.
Thank you very much. Thank you. That was very interesting. Unfortunately for the question, so I will stop the recording right now, but I can leave the session open